In this video, we're going to learn all about calculations of molarity and concentration. When you consider these two terms, you need to be thinking about solutions, as both of them are basically words to describe how much of a dissolvable substance, that's solute, is present in the liquid, the chemicals they're dissolved in, that's the solvent. In case you're wondering why it's important to know the concentration of molarity of a solution, think about this example. Imagine a chemical factory. It carries out reactions which produce poisonous cadmium metal ions dissolved in water. It pumps the waste from these reactions into a local river and regularly checks the cadmium concentration in its waste pipe. If this concentration stays below a certain level, the cadmium isn't dangerous. But if the concentration rises above this safe level, the company could potentially be causing harm to water plants, fish, and even you, if you happen to live downstream. It would immediately have to stop the reaction happening and investigate. First, let's consider the difference between these two terms. A lot of people, even scientists who should know better, tend to use the words molarity and concentration interchangeably. But this is a mistake. The difference is down to the units. When we're describing the molarity of a solution, we always mean the number of moles of solute per decimeter cube of a solution. You'll often see it written like this, or more simply like this. A cubic decimeter is also commonly called 1 liter. Concentration, on the other hand, can be written in these terms. But there are also a lot of other units popular in science to describe concentration. Here are just a few. You'll be pleased to know that the equation to calculate molarity is very easy. Molarity of a solution is equal to moles of solute dissolved divided by volume of solution in decimeters cube. In this rather large beaker, which contains 2 decimeter cube of a solution, 4 moles of sulfuric acid have been added. 4 moles divided by 2 decimeter cube equals 2 moles per decimeter cube. Or you'll often hear chemists say 2 molar. Simple, isn't it? So how about this one? 0.25 moles of silver nitrate have been dissolved in 0.075 decimeters cube of water. What's the molarity here? Pause, calculate, and resume. 0.25 divided by 0.075 equals 3.3 moles per decimeter cube. Remember to write your answer to the right level of precision using 2 significant figures. Now try this one. 0.0100 moles of oxalic acid have been added to 100 centimeters cubed of water. There are 1,000 cubic centimeters in a cubic decimeter. Pause, calculate, and then resume. First, divide 100 centimeters cubed by 1,000 to get the volume in decimeters cubed. 0.100. Then, 0.0100 moles divided by 0.100 of decimeters cubed equals 0.100 moles per decimeter cube. Okay, a tough challenge to finish. You've dissolved 0.0748 grams of sodium bromide salt in 25.0 centimeters cube of water. What's the molarity? Now don't panic. Simply use this equation, which lets you convert mass into moles, and use your periodic table to find the molar ratio of sodium bromide. Pause, calculate, and resume. So, molar mass of sodium bromide is 23 plus 79 equals 102 grams per mole. 0.0748 divided by 102 equals 7.33 times 10 to the minus 4 moles. 25 divided by 1000 equals 0.025 decimeters cubed. Finally, 7.33 times 10 to the minus 4 divided by 0.0250 equals 2.93 times 10 to the minus 2 moles per decimeter cube. Very well done if you got that one right.